Hey everybody, Mr. Klein here in a very homemade hat. It's fun. And I'm here to talk to you about differentiability. In order to understand differentiability, we have to remember two of our friends. First, we have to remember what it means for a function to have a limit. That just means that the left and the right side of the function are approaching the same thing. And then, oh, by the way, these are notes. You have them. They are in the Unit 6 packet. You should pause the video and get them out if you haven't already. All right. Second thing is continuity, which I've given you the formal definition of continuity right here, but let's just mention that a function is continuous if you can drive over it. No holes, jumps, or asymptotes. All right, now differentiable means this. It means that the function has a derivative at a particular instant. And so graphically, what that means, pick some point here. I'm going to do the fun sparkly one. Let's pick this point right here. This is a point where the function is differentiable because it has a real number slope. So another way to put this is that the graph is smooth, right? There's no pointy spots, no cusps that would make the derivative undefined, with a real number slope. Slope that you can calculate. All right. Now, the reason that we're talking about differentiability along with continuity and limits is this. If a function is differentiable like it is right here, then you have to be able to drive over it. So differentiability implies, this is an implication symbol, that a function is also continuous at a point. And let's come back up here. In order to be continuous, the limit must exist. So continuity implies that there is a limit. So that's always true. Now, in the other direction, you have this interesting effect where let's suppose that a function is not limit, or in other words, the limit does not exist. So here's an example of a function where the limit does not exist at this point. Well, if the limit does not exist, that means that it can't be continuous. And if it is not continuous, then it will be not differentiable. So you need to know that this is true, boom, boom, boom. And if you switch it around and negate everything, it's called taking the contrapositive. That's also true. All right, what else do we have here? Oh, you don't want to do that. Even bigger, even bigger. Come on. There we go. All right, so let's look at some graphical examples. Number one, we're asked to identify the interval on which the function is continuous and the interval on which it is differentiable. I always start with continuity. So here I see that this is going to be discontinuous at an asymptote, which happens to be at -2, and another asymptote, which is at +2. So if we're going to write the interval on which it's continuous, we would say all real numbers, x is not equal to -2 or 2. It's kind of lazy notation, but whatever. All right, well, so we know that the differentiable is going to be the same, except for, are there any places where the derivative wouldn't be defined besides -2 and 2? No, so this one is going to be identical. Kind of a boring example because they're the same. Next one. Right here is a absolute value graph. And this absolute value graph, I can see that I can drive over the whole thing. So this is going to be continuous for all real numbers. However, it's not going to be differentiable for all real numbers because right there, at the cusp, we can see that the derivative is not defined. So this would be differentiable for all real numbers except for x can't be equal to, that would be a -1. Didn't want to do that. Next one. Once again, we have a graph that is continuous everywhere. So we would say all real numbers. Now you would be tempted to say that it's also differentiable everywhere because there's no cusps, there's no pointy spots. But look at this point right here. Look at 2. At 2, if I was to draw a tangent line, the slope, it would be vertical. And if you have a vertical tangent, then the slope is undefined. And that means that the derivative at that point, what would that be? 1, 2. The derivative at 2 does not exist because the derivative is the slope. So we would say it's differentiable everywhere except for x cannot be equal to 2. So there's a couple of examples where you've got a picture. Now let's take a look at some examples where we have an equation. So first one right here, number 4, is a cube root equation. Now you studied cube roots before, so hopefully you remember that cube roots look kind of like this. Like a square root, but it's also got this like sort of, what would you call that, rotated tail down here. And you can see that that is continuous at all points. Now, in order to determine the domain on where it is differentiable, what I'm going to do when I have an equation is I'm going to take the derivative. So if you take the derivative of this one, you get 1/3 times x minus 2 to the negative 2/3 power. Ooh, and if we simplify that, we get 1 divided by 3 x minus 2 to the 2/3 power, right? So there's the derivative. Now look at that derivative. I see an x value that if we plugged it in, impossible, undefined. And that value is going to be when x is equal to 2, right? If you plug a, oh, what on earth was that? That was fun. If you plug a 2 into this cat, do you see that you're going to get 1/0? That's bad. So this is another situation where it's fine for all real numbers except x cannot be equal to 2. In fact, fun fact, this equation that I gave you right here is the exact same graph that I gave you in number 3. So you'll notice that we got the same answers here and here, and then the same answers here and here. That's good because they're the same function. Let's take a look at number 5. Number 5 is a piecewise function. When we look at this piecewise function, we see that it is quadratic for the first branch and it is linear for the second branch. Both of those are continuous types of functions. So if this thing is going to be discontinuous, it will be at 3. So what I'm going to do is I'm going to plug 3 into both of them. Let's see, 9 times 2 is 18, plus 7 is going to give us a 25. 12 times 3 is going to give us a 36. Oh, snap. You know what that means? That means that right here at my buddy 3, one of the functions is like this, and the other one is up here, right? There's the 36. There's the 25. So this one is continuous everywhere except for not at 3. Which means that it cannot be differentiable there either. If you have a point where you have a jump discontinuity, you cannot find a derivative. Okay, moving along. Here's the big game for today. Suppose I give you a crazy looking piecewise function, something like this. So suppose that a piecewise function is differentiable at x equals 2. So you can take the derivative at 2. But that some of the constant terms are sneaky and refuse to reveal themselves. Determine the values of a and b. Now, this is a tricky little problem because you can find, this is actually the function right here, and I have these sliders so we can play around with A and B. You can find values of A and B that will be continuous. Let me see if I can get one here. Boom, 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 boom. Like that. But if you look carefully, you can see that there's a little bit of a bump right there, which means that it would not be differentiable. So we've got two requirements here. I'll do another one. I'll try that. Boom, 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 boom. Once again, you can see that it looks like it is continuous, but not differentiable. We need it to be both. So what we're going to do is we're going to do a little bit of calculus. Step number one is start by writing an equation for the piecewise derivative. So the derivative of ax squared plus bx would be equal to 2ax plus b. And then the derivative of the second function would be 3a x minus 1 squared plus the derivative of 5 is 0. So that would be our derivative equation. Now the big idea is that it needs to be continuous, and it also needs to be differentiable, and here's what that means. Start with continuity. Continuity tells us that from the left and right side, this function needs to be the same. So if I plug 2 into the left branch of the function, we would get something like this. And if I plug 2 into the right branch of the function, we would get something like this. And I'm going to simplify that down. Let's see, that would be 4a plus 2b is equal to a plus 5. And I suppose we could simplify that down even a little further. We could subtract a from both sides. So we'd get 3a plus 2b is equal to 5. But you're never going to get the answer simply out of this equation right here. You have to use the differentiability fact too, which says that the derivative, as you approach it from the left and the right, should be the same. So if I plug 2 into the left branch here, that would give us 2a times 2 plus b. And if I plug 2 into the right branch, that would give us 3a times 2 minus 1 squared. And let's simplify that down. That would be 4a plus b is equal to, on the other side, 3a. So if I subtract 3a from both sides, that gives us that we know a plus b has to be equal to 0. So here we go. Now look at what we've got. Here's a linear equation. Here's a linear equation. We can make a system out of those two equations, and we can solve. Here we go. Almost done. I'm going to solve this one for b. Doesn't really matter what you solve for, but I'm choosing b. So b will be equal to the opposite of a. I can pick this up. I can grab it. I can copy it, and then I can bring it over here. I can plug it in right there. Ooh, and let's see what we get if we plug it in there. We would get 3a plus 2 times negative a is equal to 5. Oh, so trim that up, and we get that a is 5. If a is 5, then b would have to be equal to the opposite of 5 because of this fact right here. So there's our answer. It's some kind of messy work. Let me show you that it works. I'm going to go to my buddy Fathom here, type in a 5 for you, and a negative 5 for you, and ooh, look how smooth that graph is. The end.